everybody to this next meeting of the Energy Forum. This is co-sponsored with the U.S. Green Building Council and the Environmental Technology Center here at Sonoma State University. So glad you're all here. I think you're going to be glad you're here today because you're going to be informed and inspired for sure by the time you're out here. This is a great privilege to have Don Aitken here on our campus. Don's so well known in so many places, and he gives so much of his time that we're just very lucky and very delighted whenever he comes up to Sonoma State and hangs out with us for a while. So we get Don to come this direction whenever he can. Normally he would be driving his electric vehicle and plugging it into the building so that the building would be charging his car while he's giving the presentation. But the EV1's gone back to its maker. Exactly. So not doing that today. But Don's involved in so many projects and programs, has been involved in so many projects and programs. It's really overwhelming. I went to his website a couple of nights ago and pulled off the little introductory bio, and I just want to pull a few things out of here so that you know a little bit about Don's incredible background. He is an affiliate faculty member at the Frank Lloyd Wright School of Architecture, senior consulting scientist for the Department of Energy and the Energy Department within the Union of Concerned Scientists. Has been a staff research physicist and astrophysicist at Stanford University, where he directed 3 laboratory research projects. Was the founder and chairman of the Department of Environmental Studies at San Jose State University, right down the road, and named Professor of the Year while a professor at Sonoma State, and served as the executive San Jose State. Yeah, sorry. And executive director of the Western Regional Solar Energy Center for the U.S. Department of Energy. Well, that was way back when. And staff senior scientist for Renewable Energy Policy and Economics with the Union of Concerned Scientists. He has over 100 publications in various fields. And then, in terms of community service and professional service, an amazing record. He was national chairman twice of the American Solar Energy Society, and has twice directed their national solar conferences. Was the technical chair of the National Passive Solar Conference in 2002, not too long ago. Former vice president and secretary of the International Solar Energy Society, and was on the international organizing committee for the Solar World Congress in Australia in November of 2001. And has done a bunch of work on electric utility sector, renewable energy, marketing frameworks, architecture. Don has designed all sorts of buildings over his last 30 years or so in the field, including the Department of Energy's first solar heated and daylit office back in 1980, and more recently the national headquarters for the Union of Concerned Scientists that he still works for, which is in Harvard Square. And then Don's also been involved with the first grid-connected solar electric track home, and a very pioneering community college building down at the Anza College down in Cupertino, which just broke ground a couple of weeks ago. So that'll be up and hopefully running in the not-too-distant future. Don's a consultant, a policymaker, a lecturer, a professional architectural and engineering workshop leader, and he's done this all around the world. So some of the countries listed here where he's been involved in various education and professional training activities include Japan and Germany, Switzerland, Sweden, Finland, Denmark, Cyprus, Israel, India, Africa, Mexico, 3 other republics of the former Soviet Union. And in April 2002, Don was sent by the U.S. State Department to be the U.S. Earth Day speaker in Germany. Fascinating. So amazing. And then also a recipient of some major awards. 1997, I remember this well. American Solar Energy Society's highest honor is called the Abbott Award, and Don received that in 1977. And in 2000, he was one of the World Solar Award recipients at the World Renewable Energy Congress in England. You get the basic idea here. This is an amazing individual who has an outstanding track record. What amazes me about Don is he's been doing this for a really long time, and doing it with enthusiasm and with grace and with love and with integrity. And each time I hear him speak, I'm always inspired to be a better person, to go out and try to do more myself. he evokes within everybody that he speaks to and talks to kind of some optimism, some hope about what's possible, because really science is on our side. One of the things that you'll find out by the time Don's done today is that the data is pretty clear, the trend lines are pretty clear, and actually the opportunities for change are clear as well, and well demonstrated. And Don's been a big part of a lot of the examples that have come up over the years that said, hey, there's a completely different way of thinking, a completely different way of doing. So he's helped other organizations figure out how to do it, and he's done it himself. So he practices what he preaches as well. So anyway, it's a great honor to have him here today, and he's going to present to us for a while. We'll take a short break, and then come back for kind of a second phase of presentation as well. So that's sort of what we're in store for. AV-wise, we're in place?
I think so.
Excellent. Great timing. So would you please join me in giving a very warm round of applause to my friend and colleague,
Ordinarily, one wouldn't have to stand there and listen to the whole bio being read, but we had a technical issue. As you saw, we were waiting for the cable to arrive. So I was afraid we'd just go on reading. You could read the rest of my web page.
That's good. I could have done that for days.
This is better. I have a very nice, the color on my screen is very nice beige, so you're going to have to be working with a somewhat skewed green and yellow version here. I talked to Rocky yesterday, and at that time made the decision to take the emphasis that I'm going to be showing today. Before I do, I want to identify two people. One is my wife as well as my professional colleague, Barbara Harwood Aitken. Some of you know her because she came and gave a lecture in this series last year on her own as a nationally known builder of energy-efficient, low-income housing and solar housing from Texas. And the other one, David Deppen, just came walking in. At the very end, I'm going to be showing just a little bit about this very exciting new building that we're doing at the Vianza College campus. And David is the architect of record on that. And I'm quite honored, David, to have you show up here. That's great. And Rocky, of course, we've been buddies for a long time. There weren't that many people really in the early days of environmental studies who were really developing university programs. I developed mine at San Jose State starting in 1970. Rocky developed this one, goodness knows, 25 years ago, I guess.
Almost that.
Just about. I'm older than he is, so. And we've been mutual admirers all along. This has been a wonderful program here at Sonoma State, a wonderful program, an exemplary program. And I've sent some students up here as well. It's a great treat to be here. I'm fundamentally an environmental activist. And so I abandoned teaching in 1991 to go full-time with the Union of Concerned Scientists. And basically they said, here's a salary and here's expenses and go out and make a difference. And for an environmental activist, that's a fabulous gift. But the difference I was supposed to make is that the Union of Concerned Scientists had made much of its fame in its blowing the whistle on unsafe nuclear power facilities. And we really needed to go in positive directions. We needed to lay out positive visions and to start working with states and developing legislation for positive things. And that's what I was able to do and still am doing for about half of my time. At the moment, now, I left UCS a little over a year ago, and Barbara and I are now together. We have a web page, which is just www.DonaldAitkenAssociates, all one word, DONALDAITKEN, those are the hooker, associates.com. You can learn more about us and have access to some things. While Rocky was talking, I was looking for a report that I swear I brought. Pete, do you have that in your book? Did I accidentally stick it in your book? The European one? No. Oh, okay. I was commissioned by the European Union last year to do a white paper entitled Transitioning to a Renewable Energy Future. And I spent months on it. It's not that long. It's only about 60 pages long, but a lot of research. And it was introduced in press conferences in Berlin and Brussels last November. And you can get it through my web page under a section called Resources. And I was going to wave it around and show it here. But I wouldn't document things called transitioning to a renewable energy future if I didn't really believe that indeed that's what we can do, that we're technically ready now. And really what we're waiting for is for governments and people both to move. And so we're trying to stir governments. I spent a lot of time doing that, and we're trying to stir people. And part of the story has to come from an absolutely secure knowledge. First, a secure knowledge that this is an incredibly important time. Climate change, global warming are incredibly serious issues about which there is no doubt, underlying no doubt anymore, as to the influence of humans on those issues, human behavior on those issues. And then the second thing is the absolute solid knowledge that we can build an energy structure for the country and for the world entirely out of renewable energy, and that buildings play a major part of that. Now, there's not time in this talk to do all three of those things. When I was here not long ago, actually, and gave a lecture for Sasha's class, has any of you seen that before? A couple of you have. Where I went into renewable energy, different kinds of renewable energy, wind, biomass, geothermal, and the various solar technologies, and walked through the scenarios and the visions that showed how we really can make the transition. And my white paper will take you through those. But today, since it's part of the U.S. Green Building Council program, and Barbara and I are both members, our Aitken Associates is a member of USGBC, the obvious thing to do on the second part of this is to stress buildings. And so in the first part of the talk, it breaks into two parts. The first is to set the public policy stage. I want to talk about sustainability and climate change and energy policy. And the reason for doing this is not just to present the usual litany that you hear about, yes, climate change, global warming can cause this problem and that problem and that problem, but to document what we know about those various issues, and to document what's been fascinating progressively from the year 2000 up until last week in Seattle, Washington, at the AAAS meeting, the evolution of things that scientists are willing to say about our knowledge of climate change and the role of humans, of people, in bringing about changes on the entire face of the earth. That's the first part. And the reason for doing that first part is so that when people talk to you about climate change as being the mother of all environmental problems, which it sort of just about is right now, that you will truly believe that and truly understand that we have enough evidence now to demonstrate clearly that this is the case. Then when I go into buildings, you've got a lot of people in this series who are going to be talking about architecture and details of buildings. I will be showing you a lot of pretty pictures. But in each case, what I want to show you is as we go toward our sustainable buildings, and our buildings that use daylighting and natural ventilation and natural energy sources and so on, all of that helps to mitigate climate change. But the benefits for you from those kinds of buildings transcend hugely the energy benefits and the emission reduction benefits of the buildings. One of the greatest gifts to human societies these days are the very solutions for climate change and global warming, because they will enhance the value of our buildings. They will enhance the productivity and create more jobs in our society. They will enhance the opportunity for greater equity between societies. All the things that we need to do to mitigate this great worldwide problem are precisely the things you would want to do anyway to make us a better world, a better society, a better economy. So, between the two, we'll have a break. We're starting later than I'd expected here. I'm going to try to cover a lot, and it's fairly dense. If you have a burning question, would like to interrupt me, please do. What Rocky said, he wanted me to try to leave time for discussion. By the time I put these two halves together and we're starting late, there isn't going to be a lot of discussion time. I'm quite willing to stay afterwards for a while for one-on-one, and you may interrupt me. And if it's something I can deal with quickly, I'm happy to deal with it. If it's going to get us off in a tangent or something long, I may ask that we continue. So don't be shy. I've been a professor for so many years that I'm absolutely comfortable in being one-on-ones with students in the class, as well as public. So here we go. The definition of sustainable development that is commonly accepted. Sustainable development is development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And to get ahead of myself, that's an absolutely meaningless definition, so don't even bother to write it down. It's a definition that doesn't give us anything to go on. It's fundamentally flawed definition. Why is it flawed? Well, there it is to remind you. First, whose needs are we to meet? Does this mean that everyone in the world is going to live like Americans if you believe the ecological footprint work done by Maki Spakanagel and his associates? That means we need 4.5 to 5 Earths. so that everybody can live like Americans? Something wrong with that. Or everybody live like Ethiopians? Yeah, we could probably do that. Do we want to do that? No, but we can meet those needs. So the word needs is the undefined word. Without being able to define needs, the definition can't lead us to any specific action or any specific measures of whether we're doing the right thing or not. So we got to have a new definition or a new approach toward sustainability that can serve as guiding principles for us. Well, for example, and notice here's a typographical error. What the heck? It was late last night. One can certainly argue that the United States and the world need fossil fuels. Okay, but do we need them to meet essential human needs, or do we need them because we have a right to buy SUVs? Right? What need are we meeting? As we buy and drive our SUVs, how much are we robbing the future of being able to meet the most essential human needs in other countries? Okay? The need for oil is one that cannot be fulfilled into the future. So oil and all fossil fuels are inherently unsustainable. And this is a very interesting chart with some numbers behind it, and then all the projections of the future, of course, are best guesses. But it shows pretty much where we are in 2003, 2004, and somewhere not far away, demand is going to exceed supply. And all living hell is going to break loose in all different social and economic ways. And it's not that we're going to run out of oil, it's just that demand is going to exceed supply. The best guess these days is probably 2015. That may be pushed out as long as 2025. It may be as short as 2010. No one quite knows, of course. But look what a short time period of that is. That's all within one generation that we're going to hit that point. Most significant economically is when the world oil economics will change. And that is what they call the big rollover. And that is when we go for an oil buyer's market, which allows us to keep all of our oil costs and energy costs down, to the seller's market, and oh boy, will that change fast. And not only will oil costs increase, but other energy costs will all be dragged along with it. And we're very close to that. We don't know how close. Again, best guess, 2015. It's about the best guess I can make from everything that I've read. We're remarkably close. Well, an energy resource availability is a national security issue. Fortune magazine of last month, January 26th, really getting pretty current, had an article about global warming and climate change and national security. Wars over resources were the norm until about 3 centuries ago. As the planet's carrying capacity shrinks, an ancient pattern reemerges, the eruption of desperate, all-out wars over food, water, and energy supply. If we become short on any of those essentials, what do? We go out and get them. And starving people go out and try to get food. And countries that don't have water go out and try to annex places where they can get water. And countries without energy are going to go get energy. And so finally, well, the Bush, I got to be careful not to say all the things I like to say about the Bush administration, but they just are not taking climate change seriously at all, as you well know. But as the Pentagon begins to look at the potential disruption in international stability, that may finally be a way of getting into that administration and to start being heard. Well, we could go after more domestic oil resources, such as the proposed new Alaskan pipeline, which they call ANWR. And here's what it would do for the U.S., right there. Okay? All of this debate in Congress, I mean, Bush now is ready, they're reintroducing the energy bill, and they're just trying to get it in because we've got to be energy independent. That's the energy independence he's talking about. I mean, it's trivial, it's ridiculous, it's a total non-issue, and yet somehow it becomes the public and political issue. Well, we're turning to natural gas and making it, there are good reasons for that. It's a clean fuel, a lot cleaner than coal, for example, for making electricity. But when we look at the North American natural gas reserves, it also looks dismal. We don't have the natural gas resources. So we say, well, we've got Canada up there, and we've got other resources, we'll go after them.
What was the scale of that graph there? What year to year?
This 2036,
Okay.
basically, just pretty much continual decline is the best guess. How secure is the U.S.'s natural gas supply? Well, the cheap, readily available U.S. gas is already gone. Okay? Canada has announced it will not be able to increase exports to meet growing U.S. electric utility demands. It's only going to be able to meet its own growing demands. Oh boy, now we can't import it there. 2/5 of the world's natural gas supplies are in Russia and its former satellites. We're talking about building new LNG facilities and bringing this stuff in. Fine, where are you going to bring it from? Russia and its former satellites? Or 1/3 of the world's natural gas supplies are in the unstable Middle East. So not only will we import oil, we'll import natural gas. How do I know that? Because if you add up all of the utility plans for new natural gas power plants, you exceed the amount of available natural gas by roughly a factor of 2. We need roughly 100% more natural gas than we have just to meet the plans that are now being announced for utility power plants. This whole thing is a ridiculous, unending circle, sort of like the image of an animal biting its own tail and just going in circles. So the fossil fuel era, that's what we will now call it, is an unsustainable transition between sustainable non-fossil fuel agents. Putting this, you asked about the calendar a minute ago, now I've really stretched it out, all right? So here we have American Revolution. This is about anywhere between 100 and 200 years width. And that is the world use of fossil fuels. And up to that point, the full development, the industrial development, social development of the world was powered by renewable resources, largely wood. Then we went into coal and began using coal, and up we went to oil, natural gas, and we'll come back down, and we will have a new sustainable period after that. So the silliest thing we can do is to keep looking for new fossil fuel resources so we can just prolong the time. The time for what? The fossil fuel era that we're now in is a remarkably fortunate transition, because where we now have many people in the world who want to live with social equity and opportunity and want to have food and clothing and shelter, and it's going to take an enormous amount of energy as we move forward in time. And we need to be able to extract that energy from naturally available energy resources, which we can do. But it takes energy to power a transition. We use the energy from wood in order to make the devices that tap into coal. We use the energy from coal to smelt the steel to make the towers and derricks so we can start tapping into oil and gas. So you use today's energy resources to power your way into the transition. So the fundamental, the chief thing we should be doing with the fossil fuels is making certain that each step we take is using these precious fuels. We're yesterday's sunshine, incredibly lucky to have them. But using those fuels to make sure we have a graceful transition. If we don't have a graceful transition, we will have chaos. If we do have a graceful transition, this world can be a much, much better place than it is. So let's return to the ultimate basis of sustainability. There it is. We have a model. How do we handle that model? First, we understand the rules by which the planet works. Okay, this is the whole field of environmental studies. Everything. Understand how the natural world works. Second, we learn to adapt human activities to those rules. If we do that, we've got a fine synergy. And third, we define sustainability in agreement with operating within the rules of the way with which the world works. That's how we define sustainability. So let's try Earth System's definition of sustainability that can work. To say that a development is sustainable means at least that its patterns of production and consumption can be reproduced indefinitely without doing irreparable damage to essential natural ecosystems. The stability of those ecosystems is required for the stability of the future functioning of the Earth itself, and of course our interaction with it. So now that's a measure, because you can ask yourself, whatever you're doing, is that potentially going to lead to a degradation of ecosystems, air, water, biological resources? Or is it in a way that can work compatibly with it, like using natural energy resources, or restoring and revitalizing soils and forests? Okay? So there's a measure. So now let's turn that measure to energy. See if the present use of fossil fuels can meet this fundamental requirement of sustainability, and it really can't. All the uses of energy end up with emissions into the atmosphere, mostly into the environment rather, mostly the air. And some of you may realize that what comes out of the tailpipe of your car is 3 times heavier than it was in the gas tank. So for every 7 or 8 pounds of gasoline in your gas tank you burn, you send out 20 pounds of CO2 out of your tailpipe. It's an enormous amount of stuff going on. Okay? Well, this is really sort of what's going on. The world operates this way, where the CO2 is absorbed through photosynthesis in order to produce all of the biological matter, if you will, the biomass of the world. And then the trees themselves create oxygen and respire. They also use oxygen. Right? And you have a continual closed cycle. And when you have decay, of course, what's left goes. But you don't always have decay. A little bit of sand comes over, dirt comes over, something. And some of what should have finished in a natural cycle didn't finish. It got kind of stuck. It didn't get to decay. And ultimately, over time, that captured solar energy that drives that photosynthesis became the fossil fuel. It's just an accidental capturing. It should never have happened. A little tiny perturbation in an otherwise continuous system. Now what we're doing is we're burning that. When we burn that, we release the CO2, and one of the arguments that the coal people will say is we're just completing what nature didn't complete on our own. We're releasing the CO2 now that should have been released during decay. So why worry? Well, because of two things. First, this other stuff comes out when we release it the way we release it. And secondly, we're releasing 500 million years worth of accumulation in 100 years. And the pace at which ecological systems are asked to absorb insults is just as important as the nature of the insults. So here's the stuff coming out that nature doesn't send out. We're getting pretty good at getting rid of what we can see. When we go back here, though, you realize that the amount of carbon dioxide going back into the system exceeds the rate at which the natural system can absorb it. About 70% of the absorption is in the oceans. About 30% is in biological and land surface matter. And what we're discovering, as you all know, is, of course, the amount of carbon dioxide in the atmosphere is going up. Now, notice that those are parts per million. And you're dealing with an inert gas, which is incredibly important to us. It's so important you're sitting there making it. You're breathing in oxygen, breathing out carbon dioxide. And that's great. The plants will breathe in your carbon dioxide, make plants that you can eat, right? Make oxygen you can breathe, and we're all part of that. Carbon dioxide is a wonderful gas, and it's a tiny part of the atmosphere. The atmosphere is oxygen, nitrogen, argon, krypton, the main constituents of the atmosphere. This is parts per million. So why worry about a perfectly safe, normal gas in parts per million? Well, you have to start looking at the way both physical and biological systems operate. And very often it is that nutrient that is in the smallest amount that can play a pivotal role in the stability of all the other processes. You have a tiny amount of phosphorus in your bodies, tiny amount, but it's in your DNA. Oh, boy, don't tell me that that few parts per billion of phosphorus in your body isn't fundamental to everything else. So let's ask in what ways are a few parts per million of CO2 fundamental to the Earth? Well, first let's sort of look what's been going on. What's been going on is, over time, the last 150,000 years or so, the amount of CO2 in the atmosphere has been going up and down, and the temperature of the Earth has been tracking it really very faithfully. Until we get there. You don't have a laser pointer, do you? Don't run out yet.
I might. Let me dig in here.
Okay. The first thing that we see is that the current level of CO2 is higher than anything the Earth has seen at least in 150,000 years. And secondly, while the Earth tends to operate in 10,000 year, 20,000 year increments to sort of change, that's 100 years. And so one of the difficulties that the that the modelers are having is how do you model what the Earth is going to do when it's done that, when it's like a snap of a finger in geologic times? Well, the Earth is incredibly balanced from the standpoint of energy flow. The amount of energy that flows into the Earth is exactly equal to the energy that flows out. How do I know that? Well, there are a lot of ways. First, we can sort of just look at measurements that people make, and you can account for the energy coming in. 343 watts per square meter is an Earth-wide average, not just locally. And a good bit of that makes it down. 160 watts comes down here, and 103 watts goes up there. 200, maybe that's 140, should be 243. I couldn't read that before anyway. In any case, the amount that comes in, the net incoming solar radiation, is exactly equal to the net outgoing radiation. But what happens is it's absorbed, the solar energy that comes in, the sun doesn't deliver heat to the earth per se, it delivers light. And that comes in, that's converted to heat where it's absorbed, and then of course everything that's warm re-radiates in the infrared. So it's a different spectrum coming in and going out. And infrared can react in a molecular way with constituents in the atmosphere. But anyway, it's been incredibly balanced. And the reason we know it's incredibly balanced is because we're here. We're not there, and we're not there. If we had just a tiny bit less energy coming in than went out, a tiny bit, we would be as cold as Mars. If we had a tiny bit more that came in that was trapped, instead of going out, we would long ago have been like Venus. And that's going to be inevitable anyway. Within a billion years or so, we will be like Venus. The runaway greenhouse effect will ultimately be our fate. But tiny perturbations would have led to this or this. And we don't have those. And then we look at the difference. We notice that Mars has virtually no CO2 in the atmosphere, and Venus is almost entirely CO2 in the atmosphere, and begin to think maybe CO2 has something to do with it. Because all three of those planets are close enough for life. They're a little warm on Venus, a little cool on Mars, but they're quite close enough for life, as he followed with the wonderful explorers that are up there. So the theoreticians go to work and the experimentalists go to work. And they try to measure the ways in which the energy is slightly imbalanced. And they call that climate forcing. Climate forcing, the forcing agent is like carbon dioxide. Put carbon dioxide in the atmosphere, the energy can't escape back out quite as well. And so this shows that about 1.5 watts per square meter of energy is trapped that wouldn't otherwise be trapped. That's why they call it climate forcing. And all of these red things, methane, chlorofluorocarbons, nitrous oxide, ozone, those are the greenhouse gases. And all of those make it more difficult for the energy to be radiated back out. So they're all climate forcing agents. And even black carbon, when we burn, just the soot that goes into the air tends to absorb sunshine. Black gets warm. But then we have other things that also come out when we burn, and they reflect the solar radiation. And so that tends to cool us. Cloud droplet changes, reflective aerosols, and so on. By the way, that's in the current issue of Scientific American, March 2004. I made these slides last night. It's a very interesting article you might wish to read. Land cover changes again, and the sun itself, the evidence is in the last 150 years it has warmed up a little bit. Okay? So you add all of those things together, and you get this. The incoming energy from the sun reflected everything like that. The total incoming energy, about 340 watts per square meter. The total outgoing energy, about 339 watts per square meter. And there's a lot of uncertainty in there, but really, it's 1 watt plus or minus 1 watt. It's not 1 watt plus or minus 10 watts. Okay? The net result is 1 watt per square meter of extra energy that the Earth is now having to deal with that it didn't have to deal with before. So there you are. You put a little 1 watt Christmas tree bulb on every square meter of the Earth. And that's what it looks like. And you can say, what impact can the equivalent of a little 1 watt Christmas tree bulb on every square meter of absorbed energy have, for example, on the world's oceans? And the answer is startling. In just 12 years, it can raise sea level by 1 meter. Just 12 years. We talk about raising sea level maybe a meter in 100 years. All the calculations for raising sea level have been simply looking at the expansion of the water as it gets warmer, assuming that the melting of the polar caps would not be as severe. This latest Scientific American article, the one that's in there right now, completely challenges that. And among other things, you look at this picture and realize how much Arctic sea ice loss we've had already in the last 34 years. And it can trigger a very rapid melting, which can trigger a very rapid change in the ocean. Well, 1 meter sea level rise, who cares? San Francisco, all around this area, we're up on hills. If you live in Bangladesh, you care a lot. 1.5 meter rise, a 1.5 meter rise in sea level would affect 17 million people in Bangladesh, completely displace them, cause them to have to move inland. It would destroy the economy of Florida because it would, in fact, make it uneconomic for all the coastal areas as well as the Everglades and the southern area of Florida. We can economically build dikes around the Netherlands. We can economically build dikes around New York City. We cannot economically build dikes around all of Florida. What you begin to find, and I'm leading up to, is these small changes, tiny changes, can produce horrendously huge impacts with great effect on societies and great effect on economies. 1 meter sea level rise would be hundreds and hundreds and hundreds of billions of dollars of lost industry, to say nothing of the losses of the people in the low-lying nations. And this is the big, this is the one that people are really beginning to worry about right now. Because when you come up into Europe, I guess I can use this. Why is Europe so warm? England and Scotland, these areas up here, look where they are. They're opposite the middle part of Canada. All the people live there, and they're so warm, and they're warm because of this energy that's transported by this great conveyor belt, assisted somewhat by warm energy from the Gulf Stream. What happens is the warm water comes up here, and then it cools, and it sinks, and it comes back down, circulates around, picks up more warmth, goes back up. That is the great conveyor belt that, among other things, is keeping Europe livable. That conveyor belt is being driven by the difference in salinity between fresh water and salt water, in part, as well as the temperature. As you begin to melt, and this Scientific American article talks about it, as you begin to melt up in this area, you increase the fresh water, you decrease the salinity. And it doesn't take much decrease in salinity to prevent the cooling water from sinking down. And if it doesn't sink down, this entire cycle stops. How long do we have until that would happen? We don't know. But the evidence, and again talked about in that article, is that you can look at some changes in the Earth's climate that happened in 10 years, not several thousand years, but 10 years. And the evidence seems to be that they coincided with the interruption of this cycle. So things that can happen very fast, and one of the consequences of global warming could be the freezing out of Europe. Well, we look back not 150,000 years, but 400,000 years. We see this remarkable coincidence between temperature and carbon dioxide in the atmosphere. And so as scientists, we say that it is reasonable to assume that the way the Earth has operated in the past is the way it will continue operating. And if the temperature has always gone up when the carbon dioxide has gone up, it's reasonable to assume that that probably will continue. But nevertheless, we look for evidence. And so we look at the global average surface temperature and indeed begin to see a trend that is consistent with what you would expect from the trapping of additional energy that we now have. And then we try to make models. The reason we make atmospheric models is if you can model what happened, then you can project it with some confidence to the future and get some idea of what we can expect under different scenarios. And the original model for Earth temperature versus carbon dioxide was the blue one until they began taking into account the aerosols and the reflection and so on. And now our models work very, very well. And the models that we have duplicate what has already happened very well. So we can project the models to the future with some confidence. And then you can check the accuracy. The model missed the temperature of Venus by 2 degrees, missed the temperature of Earth by 2 degrees, missed the temperature of Mars by 1 degree. We're pretty good. We're pretty good with models. Okay? So you'll find there's still different models. And how warm we're actually going to be in the next 100 years or so still moves around the map somewhat depending on assumptions. But the average is a 3-degree centigrade rise, or maybe a 5-degree Fahrenheit temperature rise. And again, people will say, so what? I've heard people saying, I turn up my air conditioner a little bit, so what? Well, my goodness. Let's see. This is in the paper actually the other day. Not this picture, but the same figures I'll give you. For every 1 degree centigrade temperature rise, the snow level moves up 500 feet. So for a 3-degree temperature rise, the snow level, where snow changes to water, in other words, you've got snowfall above it and rainfall below, moves up the mountains 1,500 feet with 3 degrees. What would that do to the California mountains, then the California rivers? Well, the black bars are the present flow of the California rivers, and the striped bars are the flows that the rivers will be after just a 3-degree temperature rise, because you no longer can trap that snow melt up there. It simply becomes flooding waters in the winter that are gone. And what you're looking at is the end of the California agricultural industry, an $18, $19 billion a year industry, as a result of something as simple as a 3-degree temperature rise. Well, here's last week. Thought I'd give you a couple more quotes from that, the annual meeting they just held. Assuming only modest temperature increases, the new study that's not quite finished, is about to come out, anticipates a 59% drop in the water content of critical snowpack by 2050. A accompanied by frequent cycles of drought and spring floods. So there we are. Again, not only the end of California agriculture, but also very expensive things to deal with. We had a potential flood in Guerneville again yesterday in the Russian River.
Why spring flood?
Because what would normally come down in snowfall and stick to the mountains is now coming down as rainfall and blowing off the mountain. Okay. Change in ecosystems due to 3-degree rise in temperature. If snow levels rise, well, ecosystems are dependent upon light and temperature and moisture, the ecological determinants, right? So 3-degree temperature rise is going to have to change that too. So for example, the top diagram shows ecosystems A, B, and C distributed. When I speak up of the Northwest, Pacific Northwest, I'll say C is your commercial forestry. Those are the trees you're logging, and that's multi-billion-dollar industry. Bottom diagram shows that ecosystem A is now gone, B is almost gone, it's tried to walk up the mountain. C, all these commercial forests are trying to walk up the mountainside. And D, there's something brand new ecological interloper that's sort of come in there. But all of this has to happen within 100 years, and it can't happen within 100 years, which means just a massive die-out of commercial forests. There goes more tens of billions of industry. Remember, just 3 degrees. We're asking about 3 degrees. No, it's not just in turning up the air conditioner. Ecosystems are much more finely tuned than that. Current range of beech trees in North America compared to projected ranges after a 3-degree temperature rise. Look at that, from the green to the yellow. A doubling of the carbon dioxide content in the atmosphere is probably unavoidable, no matter what we do. The world will not adopt the Kyoto Accord in time. That would only lead to a 60% increase. A doubling is probably inevitable. And what happens, again, the coal industry has been going around saying, isn't that wonderful? More carbon dioxide means plants will grow faster and we can grow more food for the world. Well, plants don't just require nutrients. They also require moisture, light, temperature. All right? If you look at the United States and realize with a 3-degree temperature rise, you're going to have more evaporation from the soil, the calculations show a net reduction in agricultural production in the U.S., and especially severe, of 50% or so in heartland U.S. and also in heartland of California. And that is probably inevitable. Well, we would say, don't worry, we're used to importing foods from neighboring countries anyway. Well, you can forget about that. Because the doubling of the CO2, which is probably inevitable, is going to hurt the nations from which we import most of our food more than we are. All of these nations, all of South America, Africa, India, most of Asia, will suffer reductions in their ability to grow food just at the time that they need to increase their ability to grow food. You can look how bad off Mexico is. It's one of the red areas. So as we become less able to grow food for our own population, we become less able to import food. Now at this point, people who may not have been listening to me are finally listening to me. If they didn't care about ecosystems and so on, how about food? In a few minutes I'm going to talk dollars, and then I'll really be there. Okay, I've already talked dollars. So we can convert something like a 3-degree change to massive worldwide famines. That's how finely tuned the social systems of the world are to the stability of the ecological system. We're already seeing more subtle indications of major climate shifts in historic rainfall records. If you go back to about 1860 and you group the rainfall into latitude bands, and around the equatorial area it just bounces around the statistics. When you come up to the southern area, we're already in Arizona here in Southern California, where it's already pretty dry, but you have normal rainfall statistics until something's beginning to happen. And that rainfall didn't just disappear from the southern latitudes because there it is. I'll get this working. There it is right there. It moved from here to here. These are not models, folks. These are measurements. This is what's going on in the world right now. This is the shift of rainfall from the dry areas, making them drier than they were, up to the northern areas. And when did that shift start? That shift started, my goodness, around 1950. And if you look at all the curves of the increase of greenhouse gases into the atmosphere following World War II, 1950 is when it all began to really take off. So we have the experimental evidence. We have the evidence we need that the world is already responding in precisely the ways that we would expect it to respond. But this is what we're worried about. Here's the doubling. Here's the current level. The Kyoto Accord would cut us off about here. We probably are going to get there before the world really wakes up about it. Okay? Look at that. What an extraordinary difference, extraordinary impact human activities are having on the Earth. What we're trying to avoid with Kyoto and other things like that is a quadrupling of the carbon dioxide. With a quadrupling of the carbon dioxide, we're no longer growing food throughout all of the wheat area and corn belt areas of the United States. We're no longer growing food in central California. But don't worry, we're not able to buy it from anywhere else either. These are hugely important and serious consequences. So now we begin to look at the way the scientists, which are always standing back, being a little bit more cautious about what they want to say about the conclusions. So in 2001, they are ready to say this. There is new and stronger evidence that most of the warming observed over the last 50 years is attributable to human activities. That's the Intergovernmental Panel on Climate Change, the international organization. Started out being 1,500 scientists, is now 2,000 world scientists. That's a strong comment for scientists to make. Then we go to last week. So we move up. Scientific debate has now largely ended as to whether human activity is responsible for the average 1.1 degree Fahrenheit rise in global temperatures in the 20th century. The evidence is virtually unassailable, a view shared by nearly all credible researchers. That's where we are. So you'll still hear people doubting it, including the White House, saying, oh, it's not proven yet. Boy, it's sure proven to the satisfaction of the people who are paying attention and who should know. And yet, maybe this whole discussion of warming is the wrong thing. Because what does the Earth do with its thermal energy coming in? It creates weather. And weather is the Earth's mechanism for distributing energy that's unequally impinging on the Earth, especially in the equatorial areas, distributing it around. So having more energy in the equatorial areas sets up the great flows of the winds that then carries the air energy north and south, which sets up the great flows of the ocean currents as well. So maybe we should be looking at climate for even more evidence if we're not already convinced. 2001, the chairman of the IPCC said that the overwhelming majority of scientific experts, recognizing that uncertainty still exists, believe that human-induced climate change is already occurring. That's 2001. That future change is inevitable. Indeed, this is the sort of things they're looking at. Only we put it not in terms of numbers of major storms, but rather the economic cost in constant dollars, not inflated dollars, that the United States has been paying for storm-related damage. And it doesn't take much of a mathematician to see a trend in all of that. Some of this, indeed, is demographic because people are building bigger, more expensive houses that the hurricanes hit on the East Coast. At most, maybe 40% of that one is demographic. The rest is real. It's hurricanes, tornadoes, floods, rainfalls over 2 inches at a time, and so on. Huge. So we move up a year, October 12, 2002. Worldwide economic losses for natural disasters appear to be doubling every 10 years. These are the scientific statements now. The cost of climate change could soar to $150 billion a year within the next 10 years. Wow. That little bit of extra energy that we're storing, 1 watt per square meter, becomes $150 billion a year for the world. Wow. November 2003, there's no longer any doubt that human activities are having measurable and increasing impacts on global climate. You notice the scientific statements are getting stronger and stronger and stronger. Finally, the scientists are saying, look guys, we're here. There is no doubt. We want you to listen to us. We're going to use the strongest language that we're willing to state. Okay? And this is a scary part because these are the insured losses. This sort of buffers us. The insurance protects us from the personal losses. Well, look again at constant dollars at the insurance losses and payments for major storm-related damages in the United States only. And that leads to, by 2002, the increasing frequency of severe climatic events has the potential to stress insurers, reinsurers, and banks to the point of impaired viability or even insolvency. How can that be? The first picture I showed of climate was of a hurricane from the air. That was Hurricane Andrew from the air. Hurricane Andrew bankrupted 13 insurance companies, but thank goodness it went 15 miles south of the center of Miami because it would have bankrupted the insurance industry of the United States. One storm. So the insurance industry that's used to making its money based upon estimating risk and then projecting to future risk statistically so they can know how much to charge you. Doesn't know what to do. They've lost their connection to the past. Furthermore, they're paying out so much in the future, and they're still charging you premiums based upon previous estimates. They go in belly up. So overseas, the insurance industries of the world are the ones leading the campaign to mitigate climate change. Okay? But this is the same chart that we just saw again, the same one. And basically it shows the costs imposed upon us in the United States by weather-related events, and that's how much insurance is carried, and that's it. What do insurance companies do when they can't afford to pay something? They just bail out. You can't get hurricane insurance in your houses anymore out east. You can't get earthquake insurance here except really substandard stuff. Okay? December 2003. The world's biggest reinsurance company, Munich Re, has attributed a sharp increase in weather-related disasters around the world to global warming. The insurance company is saying, guys, the time has come for you to recognize that's where it is coming from. In its latest annual report, the company, which insures insurance companies, that's what reinsurance is, puts the combined cost of the 2003 natural disasters close to $80 billion a year. Wow. This little 1 watt per square meter, 1 degree or 1.1 degrees Fahrenheit temperature change? Okay. Another one. Before 1970, cold temperatures caused freezing at high elevations. Let me go back for a second. No, that's all right. That's what I wanted. So mosquito-borne diseases in plants, mosquitoes that sort of get trapped down here where it's warm. They couldn't go over the top. But it's beginning to warm. As you get the snow melt above, the mosquitoes can begin to leak over. And all of a sudden you begin to get transmission of disease. There's growing evidence that changes in the global climate will have profound effects on the health and well-being of citizens in countries throughout the world. World Health Organization now issuing warnings to us. For example, with dengue fever, this just shows the number of days, number of weeks of potential dengue fever transmission compared to now with the way it'll be with a 3-degree, I think it said 3-degree temperature rise. And you will see that you go up from, in San Diego, for example, from 12 weeks up to maybe 22 weeks of the year where you've got increased potential exposure to mosquito-borne diseases. So the World Health Organization announced that we must better understand the potential health effects, particularly for those who are most vulnerable, so that we can better manage the health risks. An estimated 150,000 deaths and 5.5 million disability-adjusted life years were caused in the year 2000 due to climate change. So this just about finishes the evidence that we have, but it is overwhelming. It's no longer a matter of scientific debate or policy argument. We have the data. We have the data on human societies and on people. We have the dollars cost, the storm information. We absolutely know what's going on now, and the Earth is responding. And will continue to respond in ways that make everything that you've seen worse unless we respond. So here's the warning. With diminishing insurance coverage during times of ever greater environmental hazards and ever more costly storm losses, the financial risks are now increasingly on our own shoulders. And that moves global warming and climate change into the realm of public policy and into the responsibility of all governments, from national to local, to reduce those risks. That'll take us to part 2. And so why don't we get up and stretch? But since we started late, I'd love to be going again by 10 after. Okay?
You can do that.
You're welcome. pretty dense stuff. The PowerPoint talk that I've given to Rocky, he has it on a CD. He can do whatever he wants to in terms of making it available for people to see. But it's being made available right now. We're going onto the web live right now as we're doing this. And you're going to be able to stream into the web later on. You want to explain that more?
They know.
You know about that?
Yep.
And so I'm going to go look and see what it might look like, I guess, on the web. But it's a good way of getting this information out.
You're really small, though, I'll tell you that. You're not that big.
Little tiny. If there's a question on some of the resources, you can ask me. I list the resources on the slides. One student is doing a paper now and needs to know some of them. They'll also be in Rocky's slides. But if you don't have them, you can contact me. He has my email. And on the web page, of course, it has how to contact us. All right, now we will give the nod to the U.S. Green Building Council, organization that's immensely effective, has totally changed, especially the LEED rating. That's just part of what USGBC does. Changed the face and the landscape of buildings in the United States to the point where, almost to the point now, where if you make a building that is not green, that is not going to be LEED certified at least, you may have trouble finding customers for it. We're very close. The USGBC conferences are drawing 3,000 people. So buildings are important in a lot of ways. And what we're going to do is just focus, remembering that buildings are not the whole solution. I'm even going to talk about efficiency a little bit. Efficiency in renewables and buildings and transportation and industry are all elements of the solution. But let's start with where do we go from here? Well, you begin by looking at the relative emissions of selected countries. Tons per capita, the United States, about 20 tons of CO2 per capita. If you go to the total country emissions, the United States still leads, all right, with around 5 million tons, but China is close behind. But if you convert China to tons per capita, they're only about 1/10 of what the United States is. So our personal impact, our lifestyle impact, is huge. We dominate the world scene on CO2 emissions, and this is why the present administration has been so unbelievable to watch it just pull the United States out as though we're not part of the world anymore. And we've got quite a way to go. So starting here in the U.S. is where we got to start. And what do you start with? You start with energy. If you look at the sources of greenhouse gases, you find that energy is the greatest composite source of greenhouse gases, and therefore that is where you want to have a policy to start to mitigate the changes. So the first task is, of course, use what we do with greater energy efficiency. I mean, that is so obvious. If you can get twice the amount of work and twice the economic activity and half the emissions and half the energy use, why not? You had a question, sir?
Yeah, what's the energy include?
I'm sorry?
What's the energy include?
What does energy include? Energy includes all the ways of creating and using energy. That's all the forms of energy.
So like, what's the industry? Take manufacturing, and start that.
I've been told also because of the microphone to repeat the question. The question was, what does that energy bar entail? It entails the environmental emissions related to the production and use of energy by industry, by transportation, by people in their homes, by commerce, by buildings. It's all of the different ways, and it includes the energy cost of getting energy. It takes about a barrel of oil to get 2 barrels of oil out of Alaska, for example. So, we clearly want to start with greater energy efficiency, and that has been helping us quite wonderfully. Back in the 70s, we were getting projections that we got to build power plants, for example, to keep up because this is the way the energy growth will be. These were the governmental projections in 1975. And oh my goodness, if we don't start building those new nuclear plants, we're going to have terrible shortages. But fortunately, that's not what happened, because we began to take energy efficiency seriously. And the economy has grown by 60%, and energy use essentially hasn't grown during that 20-year period. And thank goodness, because if energy use had grown the way they thought it would be, we would have spent $150 to $200 billion more this year for energy, just for the energy industry. And it's for energy that we just proved we didn't need to use. So that $150 billion has now gone back into schools, and hospitals and infrastructure and everything else. So energy efficiency is marvelous for the economy. We've been doing pretty well, but projections do show us growing. But it's also a national security issue, and there's an extraordinary article in Fortune magazine on January 26th on the relationship between climate change and national security. And just a few of the points from that. Climate collapse. It's the Pentagon's weather nightmare. That is the title of the article. And all of a sudden, the Pentagon is beginning to pay a lot of attention to the global insecurities that can begin to arise from climate change. The climate could change radically and fast. That would be the mother of all national security issues. Okay? As abrupt climate change hits home, warfare may again come to define human life. And when the Pentagon starts realizing that, all of a sudden people in Washington start sitting up and taking notice. If they didn't believe the environmentalists, maybe they'll believe the generals. Okay. Energy efficiency is a security issue. Climate collapse. I just did that. Sorry. So the more significant question is, which is better? Energy efficiency or war over oil? Alas, we digress from this talk. Returning to the topic at hand, but I have made my point. Okay. One way to get more oil into our economy is to develop more domestic sources. We showed you how much you could get with a new pipeline. This is the old pipeline. This is the existing Alaskan pipeline right now. Okay. Another better, cheaper, and faster way to get more oil into the economy is to use what we got more wisely. For example, suppose, to show the power of this, suppose we weatherize our oil-heated homes. Okay, we just go to those oil-heated homes in the Northeast and in the Midwest that are not weatherized, and we weatherize them. The amount of oil that we would save would be equal to, the Alaskan pipeline. So we just invented a new pipeline by weatherizing homes that use oil. But there's another way of looking at it. It means that about an Alaskan pipeline's worth of oil has zero economic value, because all it does is to make energy that leaks out through walls and windows. That doesn't create jobs, because the power industry doesn't do anything for you. It leaks. And so what happens with energy efficiency and energy conservation is you bring the energy resources back into productive economic use. This, again, is why it makes sense for governments, for us to have government subsidies to support conservation and efficiency standards, because that gets the wasted energy dollars back into the economy to be used for productive means. So then we go to buildings. Buildings use 1/3 of the nation's primary energy. And if you take into account the energy used to service buildings, to go there and back, for example, bring goods to and from buildings, you can account for almost 50% of all the nation's energy use, directly or indirectly related to buildings. But what do we see buildings as? Buildings are boxes within which people are doing important things. So we see the buildings as just what's going on inside the building. But now we're beginning to look at buildings, the boxes. What influence do they have on us? Buildings use 2/3 of the nation's electricity. 2/3 of the nation's electricity. When we had our so-called electricity crisis, which we knew at the time 2 years ago, we knew it was all market manipulation. We knew it. I was the intervener for the Union of Concerned Scientists at that time at the PUC. We all knew what was going on, but the public didn't, and the governor panicked and said, build more power plants. And we knew at the time that with efficiency we could have dealt with it, because that's where the electricity is going, in the buildings. Buildings contribute over 1/3 of the nation's greenhouse gas emissions, generate 40% of the nation's solid waste. A 30% improvement in U.S. building efficiency would reduce energy bills still further by $75 billion. Wouldn't that be wonderful to get those back into schools and hospitals and infrastructure and creating new jobs? It would eliminate the need for the equivalent of 80 new nuclear power plants. We only have a little over 100 right now. So all you got to do is jack up the efficiency of buildings by 30%. Piece of cake. If we can't design new buildings now that are 30% better than Title 24, which is the nation's most stringent standard, we might as well quit designing buildings. Not quite. I look at David Deppin. It's not quite a piece of cake because Title 24 is pretty tight. But average over the United States, yes. If we can't go back into existing buildings and save 30% by changing out the lights and changing out the HVAC systems and so on, better fans, all sorts of things, Okay? We should quit trying. It's easy, easy. This is easy stuff that either doesn't cost anything or pays for itself. 30% improvement in the U.S. building efficiency would displace anywhere from $40 billion in new power plants if they're gas-fired, or $400 billion in new power plants if they're nuclear powered, which is what we're beginning to hear about more and more, aren't we? Okay? And if you don't have to build those things, you got $40 billion or $400 billion or somewhere in between that you can pour into creating jobs and other good things for society. That's what efficiency can buy you in buildings. But there's so many more societal benefits from sustainable buildings than just energy and cost saving. So what I'm going to do now is we're going to walk through a lot of examples of sustainable buildings, but show you what you're getting that's more than just the energy savings and the greenhouse gas mitigation. And partly it's because these other benefits are the things that we do to be able to sell the buildings to government, to sell the buildings to our clients. Very famous building, Lockheed Missiles in Space, designed 1983-84 by Leo Daly Associates. Lockheed said, we have 3,000 people here, we want to move them over here, and they took the footprint of Leo Daly Associates in San Francisco and said, please design us a thing over there that'll put the 3,000 people in. And Leo Daly said, okay, but if you pay us for 2 weeks extra, we think we can design you a better building. And Lockheed did do that. And the result is one of the most world-famous daylit buildings and energy-efficient buildings in the world. Reduction of lighting energy use by 70%, other energy use by 50%. And the main key to that is daylight. And displacing electric lighting by daylighting. Look, okay, here we are. In fact, a little less daylighting would make the picture look brighter, but I don't want to shut this down. So
We can do that.
no, it's fine. Lockheed throws daylight farther than any other building that's been designed, 90 feet, by bringing it in off the south glass, bouncing it off of that light shelf there, up to the ceiling into the building. There's the key to daylighting design, and we all know that now. If you've got to bring the light in from the side, you throw it up at the ceiling. The best thing is bring it in from high if you can. If you can't, make it go high. There you are. There are 2 architectural principles for daylighting design, along with a few other things, getting rid of heat, glare, and things you have to think about. But look how amazing this is. Now, 3,000 people in Lockheed, Building 157, working in cubicles that are daylit, but they can't see the windows, because they just reflect the light up to the ceiling and then bring it down to the cubicles, and they're working on these wonderful shadow-free environments. And the result is that people love to work there. When you get to the inside, then where the daylight falls off, Lockheed put in what we would call an atrium, but Lockheed called it a lightrium. And people go in there and they eat their bag lunches and they have chamber concerts and they meet with each other and they love the building. And so Lockheed began to document their experience for that building and found some remarkable things. This is the first paper published, and I published it actually as a newsletter because the president, the CEO of Lockheed was a personal friend of mine and allowed me to get some data, and I published it in the later 80s. Extra cost of $2.5 million that was expected to be paid off in 5 years at $500,000 energy savings per year. So that was Lockheed's justification. All that wonderful daylighting is going to save us $500,000 a year. 5 years, we've got the extra cost paid off. Isn't that great? That's not what happened. Reduced absenteeism of 15% paid all the extra costs in the first year. People suddenly didn't have headaches. They enjoyed working in the building. Working in front of the computers was fine because the electric lights weren't flickering on the computer screen and so on. Sickness and absenteeism went down. And you pay 100 times as much per square foot for the human being working in the office as you do for the energy to condition that square foot. Therefore, the reduced absenteeism, boy, paid off $2.5 million in 1 year. It was done. The improved employee productivity swamped the economic benefits and energy savings. This started now what's been a whole series of documented stories that people have been looking into ever since. Higher employee productivity in Building 157 enabled Lockheed to win a contract from which the profit bought the entire building in the second year. They were able to charge lower overhead and less labor hours, taking into account that 15%. That was just enough to make them competitive enough to win the contract. That contract had enough profit in it about the whole building, $40 million for the building, second year. And they attributed all of that to the daylighting and energy-saving design of the building, and they had never expected that would happen. Well, we've learned a lot from that, and I can't take that long to go on all the other ones. I've designed some buildings in the area. I designed a new building for Sunset Magazine, their offices in 1985. And I clearly wanted to use daylighting. They wanted 45,000 square foot building, and original design was a building. And I couldn't bring daylight everywhere. And I said, this is Mediterranean climate. Let's do a Mediterranean courtyard design. And you can stack one part on top of the other. Nobody's more than 20 feet from a daylighting source. And there was the building. And you bounce, maybe you want to get daylighting in. So the walkways are resources for bouncing the daylighting in and up to the ceiling down below, for example. When you go upstairs, they wanted to have a long sort of overhang with shingles because it's a residential neighborhood where they are. And I just took the walkway and extended it out and made a light shelf, and the daylight semi-bounces from there up. And also I wouldn't let them put plants everywhere in here, because this is also part of my daylight reflection. And so the combination of there and there going into the windows, and the next picture is inside, and there it is on the ceiling. So I got it, yeah. So now they don't have to use the electric lights. And we learned quite a bit from that. First, it was the first commercial building in California to use daylight combined with groundwater cooling. I wanted to use natural ventilation cooling, and then I found that 110 feet down we had a 55-degree water source that was really quite accessible. And so we just bring it up, cool the building, and put it back down. And instead of costing $55,000 to air condition the building, it only cost $18,000 to dig the 2 wells and put in the pipes and pumps. And the net result is it produced the most energy-efficient building in California for the rest of the 80s, a building people love to work in, and built for 0 extra first cost. No extra first cost. Payback was immediate. Why? Because I took the cost savings from using groundwater instead of air conditioning. I put it out to make the bigger walkways and to use better glass and better lights, and we're done. And this, for those of you who know about whole building design, is exactly what you do. And this is why we can make these remarkable buildings now. The green buildings in the United States, the survey that they've made most recently, shows that the average cost increase for these remarkably performing buildings is 2%. It can be as high as 10%, as low as negative, or 0. And the average cost is 2% because you're moving budgets from one part to another. As you make the building envelope better and better, the mechanical systems get smaller and smaller, they get cheaper and cheaper, you move the money out to the envelope and make it better, and da-da-da, and you go. And they simply show that sort of thing. Now, for a more recent example, Bill McDonough's headquarters of the Gap in Burlingame, right where Highway 380 and 280 come together. Very easy to see when we go visit. Okay? And Bill designed it for all sorts of things, including recognizing that when you've got people working in a building, what you want to do is make them comfortable. The building does not care if it is warm, and it doesn't care if it's cold. Only the people do. So instead of having to heat and cool all this mass of air to keep this person comfortable, you just bring the conditioned air in right up from below. This is becoming increasingly popular. Now the air comes there, the person sitting there is either warm or cool. What does the air do? Then it takes the rest of the hot air and all the other unhealthy aspects of just human beings, the emissions from human beings even, just being in buildings, takes them up to the top and out they go. And then he used daylight very carefully in the building and a lot of other features. So that's how the building looks like from behind. He did careful daylight diagrams in order to design it in a way so he could throw the daylight in all the spaces inside. And this is the result. It's in the cafeteria area of the building and in the atrium of the building itself where they could grow green plants and have a lovely place to go. And Gap has been documenting their experience, like Lockheed. Higher productivity of employees in the new building. Indeed, frequent requests from employees in other buildings to co-work in the new building. There's a competition. And the Gap has also indicated that the building has been paid itself back long ago by increased productivity and joy of the people working in the building. Okay? By the way, it saved energy. And since it saved energy, it reduced greenhouse gas emissions. Isn't that wonderful? At the start of my talk, it appeared that that was our aim. It still is our aim. But you don't have to worry about it. Just do your good buildings, and they will do the emission reductions for you. That's the thesis here. I designed the national headquarters for Union Concerned Scientists. We had a sort of squeezed-in site here. It's at Harvard Square. Harvard University is right here across the street, and the Harvard Square is over here. And this building we sort of squeezed in behind there, a little 6-story building. And any building I design, the windows will open. If I work with an architect or an engineer and they say they don't want the windows to open, I'm out of it. It's just ridiculous. There are a lot of reasons why you want to have the windows open. One is just personal. Isn't it nice to open the window and smell the fresh air? That's just personal. But that increases productivity. Second, you only open the window if it's not too hot or not too cold outside. And therefore, the energy impact is just negligible. Okay? Third, what do you do if the electricity goes out? Well, if you've got sealed-off windows, pretty soon your office becomes so stuffy you have to go home. This is a building with daylight in the windows that you open. Electricity goes out, pop the window open, breathe the fresh air. The daylight provides the light. If you're smart enough, you have a laptop, which everyone in the Union of Concerned Scientists now has. So if the electricity goes out, it doesn't make any difference. You go around working in your office and you're comfortable and healthy. Bringing the daylight up to the ceiling, and another trick is allowing the daylight to walk into all spaces from the ceiling, which means that you don't have opaque surfaces beyond a certain height. People want their own offices. I say, fine, you get the wall to 68 inches. I get it above that. And so the result of that is the daylight can come from all directions simply going through the glass. There's another result. It saves 40% in the installed lighting power density just by having the glass. Because when his light is on, I get some of it. It's not all lost in his office. Okay? And then try to bring in, we've got to have walls, bring in a farther interior. People who were going to be in the interior offices were all noses were out of joints because you guys are going to sit on the perimeter and you're going to have all the daylighting and we're going to have this interior office. And I said, just relax, just relax. And those are the interior offices, just more glass, that's all. So everybody in that building has not just access to daylighting, but views to the outside. And those are the two critical elements. Not just daylight, but the views. And when you're deep inside a building and you don't have a useful daylight light, if you can still give a view through a clear story to the outside, you've done a great deal to the psyche of the people inside. So you're designed for daylighting and views inside. And this is the reception area. This is on the 6th floor, so I can put a skylight in there. As long as I was putting the skylight, then I could put in a stairwell connecting the 6th and 5th floor and let that just be a daylighting source as well. And you'll be in this building for a couple of hours before you realize you didn't see any electric lights on at all. Of course, it has electric lights if you're on the night job. And being a scientist, any building that I design, we monitor. So the building has been monitored. Measured 70% lower energy use for heating and cooling than California standards. It's not in California, it's in Cambridge, Massachusetts. Wow. Measured 92% lower energy use for lighting than the California standards. It uses 0.25 watts, 1/4 of a watt per square foot of lighting power density, is the measured year-long value of the electric light. The lowest energy use for lighting ever measured in a U.S. office building, and all within the original building budget. No extra first cost. Now, you can't always be that lucky, but it does say that a lot of the time you can be. Sorry I'm bragging about it since I designed it, but no matter. Now, things I didn't design. Let's go away from office buildings. Go to other things. Consider retail. Bullocks came into San Jose, California in the early 70s. I forget the date, so I didn't put it. And they bought this building that had no windows. Remember in the 50s and 60s we were making buildings with no windows so it wouldn't distract kids in school and wouldn't distract people? Wow. And Bullocks was smart enough to core out the inside of it and put a tensile fabric structure. They just carved out a big chunk of the roof and put the tensile fabric structure up there. Then they found something rather interesting. Sales went awfully well underneath that tensile fabric structure in the daylit area. So they began moving different store departments into the daylit area and found that it didn't matter what you put in the daylit area. It sold better than it would anywhere else in the store. And the number 15%, which keeps coming back over and over again, came out here too. They had about 15% higher sales of anything put in the daylit area than otherwise. So, what was their experience? Sales of merchandise in the daylit area increased by 15%. You increase your sales by 15%, it swamps your energy benefits. Sure, it's nice to save energy with daylight in, but whoa, you got more sales. That's your bottom line. Sales of any merchandise put in the daylight area increased. Walmart did not escape Walmart's notice. They tested skylights in their original store, and they put skylights in one half and not in the other half, and found the same thing. People would come in and turn right and go down to the daylight area and shop. Okay? Wow, these are significant. Real Good Solar Living Center in Upland, California, designed by Van Bryan Associates, and David Deppler, part of that team and that company that designed this wonderful building. A lot of great features in it. One of the many being the wonderful natural ventilation, natural cooling, and natural daylighting. Now this is in a place where the temperature gets over 100 degrees in the summer, like here. In fact, in Marvelous time, I was privileged to be with Rocky here when you christened this building, remember? And you were smart enough to cool it at nighttime and leave it cold. Remember how hot it was? It was 100 degrees outside. And people would come in the building started out like 68 or 70 degrees just from the natural cooling. And they were telling him, you know, I think the air conditioner was too low and not too much and all that. Same thing happened in this one. People will go in when it's 100 degrees outside and 75 inside and demand to see the manager, saying this is supposed to be an energy-saving building. Your air conditioner's turned up too much, and they'll say we don't have an air conditioner. Okay, that's last night's nighttime air cooling it. But here's the bottom line for utilities that do the green building. I'm sorry, for salespeople. What am I trying to say? Retail. Utility bills for the Real Good Solar Living Center are 90% lower than the utility bills of a conventional building. That's great, but there's the biggie. In-store sales the year before were $700,000, and after opening the store, they doubled. 50% over their projections, because people came to experience the building. There's the bottom line. The building is incredibly energy efficient. It uses little energy. It contributes. It's a great contribution to mitigating greenhouse gas emissions. But they don't have to think about that because this is their bottom line. The other stuff all comes for free. The reason I'm showing you these over and over again is we keep getting these full-page ads, for example, by the coal industry and by other industrial organizations that will say, don't sign on to the Kyoto Accord in the U.S. because it's going to cost hundreds of billions of dollars and it's going to cost us millions of jobs. And what I'm showing you is it's just the opposite. It becomes money-making and creates jobs. Daylighting in schools. This is how we did it for quite a while. This school has got the gall to name itself the place of the sun elementary school, even though they left the windows out. But it turns out we were still doing it right in California in the 1950s. And a very careful analysis was made by Lisa Heshon, who's recognized down here in her group, of the benefit of daylighting on kids. She went and surveyed 20,000 kids. And they did all kinds of tests to look at performance of the kids in their relationship to windows and daylight. And this is what she found. From comparing 20,000 students in studies that started in North Carolina, but were really done in California. Improved test scores by students in daylit areas, 15 to 26% faster learning rate by students in daylit areas. What are schools for? They're for promoting learning. Well, when I was the keynote speaker to the New York School Board Authority, and I showed them these statistics. And I said, I'm still getting from schools that if it's going to cost 1% or 5% more to build a daylight school, you won't do it because you can't afford it. What you're telling me is you want to build a school that for 50 years will be substandard in its ability to educate your students. You are electing to do that. Because we now know that daylighting in schools, universities, everywhere, dramatically promotes learning. There's still more. We don't just have to have light from the sun, we can use it for heat, and I've got to go pretty fast. So we've got passive solar heating, if we're smart enough to put our windows on the south side of our homes, for example. We get the light in the home, but we also get the heat. This is what a passive solar tract home in Reno development looks like in Reno. And simply it's got quite a bit of glass facing south, and yes, you do lose heat out of the glass at night. You do lose heat when there's snow on the ground and it's gray, but you gain more heat back than you lose when the sun comes out. That's all you really care about. Okay? So the relative suitability for solar energy collection year-round for passive solar heating doesn't say fair, moderate, not good. It goes from excellent, very good, good to fair. Seattle, Washington is fair. That means 30% to 40% of your heating from passive solar. It's easier everywhere else. Right? Solar water heating. Sure, it's simple. Do it for residential. When I was at San Jose State in 1976, I sort of blew my sabbatical year to work on this with the students. But we converted 3 dormitories, created a 9,000 square foot set of solar systems that produced 15,000 gallons of hot water per day, so 3 dormitories. That was all the water heating that the dormitories needed. This at the time was the largest solar water heating system in the United States, and it was built by students as a supervisor. Fabulous project. Certainly works in this climate. So then I got an opportunity to design our new library at San Jose State. And I thought, wow, I mean, solar water heating works so well these days, and solar electric was not at all cost-effective in those days. But I still designed the first building integrated solar building anyway in the state. And what I did is design the library that has no mechanical systems. It has no heating system and no cooling system. It's the first building that the state allowed to be built with no mechanical systems. 4,000 square feet of this stuff, the solar water heaters, is what provided the heating and the nighttime climate and the construction of the building and all the cement that we used and the careful placement of windows and so on provided the natural cooling. And I thought, wow, this is the late 70s. We now have done a building on the Bay Area to show that you can actually do buildings with no heating, no cooling systems. The climate can do everything. And I naively expected that that would take over like wildfire. Well, there it stands alone, although we've still got some buildings. But more recently, we're getting evidence that people are returning to the idea of using passive solar heating as one of the elements of the building. And one of them was rebuilding the old warehouse. The California Center for Arts and Crafts in San Francisco rebuilt this huge warehouse. I think it's 100,000 square feet. I don't quite remember. Do you remember, David? Something like that. And uses it. And there's the drawing for it. Not only rebuilt it, but they dug up the floor and put in a new radiant heated floor. And then they put solar collectors up on the roof, and they get 60% of their space heating for that building in San Francisco. And this is completed just 2 or 3 years ago. So what was a good idea in the 70s is still a good idea. It still works. So there's something else we can use to help our buildings. They had a wonderful opening in the building. Okay. We can also tap into solar energy to make electricity directly. You know about that. But you have to cover up our fields with PV arrays or wind turbines to collect that renewable energy. I just thought you might like to see that if you take 10% average efficiency of PV and say, let's make all the electricity for the United States out of photovoltaics, that's about as much land as you would need. Well, it's still quite a bit of land. Would we be willing to devote that much land for something socially important like electricity? Well, since it's only 1/4 as much land as we've already devoted to roads, the answer is probably yes. Is meeting all the electricity needs of the United States 1/4 as valuable as having roads to drive our cars on? Probably yes. So there are ways to start finding the land. This is just a world version of it. If you powered the world with photovoltaics, the World Bank did this one, the amount of land that it would take is somewhere between groundnuts and seed cotton. The little orange bar you see. But we let our building surfaces be our solar land for building integrated PV. This system has been going since 1986. If people wonder how long they can go. What's the power of the solar energy falling on roofs in the San Francisco Bay Area? This happens to be in Orinda, California. There's a 12 kilowatt system that covers 3/4 of the south side of the roof, so 3/8 of the whole roof. That's enough to provide for this 4,500 square foot house and both of their electric cars. So the amount of solar energy falling on less than half of your roof can power 2 cars and your house. With today's technology and today's efficiencies. Yesterday's design approach to buildings was to shield them from the environment. Today's design approach is to use all of the surfaces and use the surfaces whenever you can to talk to the environment and to meet building needs through this conversation with the environment. So we're getting PV electricity for local stores, for example, on the roof. Palo Alto Hardware, 90% of their electricity from solar electric. Chabot Space and Science Museum, solar electricity on the roof to power the telescopes. Moscone Center in San Francisco, almost 700,000 watt system. And by the way, it's being paid back. It's a revenue neutral system. I can't go into enough detail here, but they did an energy efficiency conversion along with this PV all at the same time. They made that one economic package. The net result of the energy efficiency is paying for the cost of the PV, and it's revenue neutral. It's not costing the citizens of San Francisco anything to do that. 1 million watts of PV on the roof of the Santa Rita Jail. Solar electric lighting in the Berkeley Whole Foods grocery store. We walked down to that grocery store. We live right, Barbara and I live right around the corner there. Very interesting because those lights are direct current. It's the only DC system in this area right now. So when the AC system goes out, the lights are on. Okay. Back up to the roof of the Union of Concerned Scientists near National Headquarters, we only had a little roof left over. So we put 2 kilowatts of PV up. It's the same amount that you've got up here, although it's a different technology. 2, we have 3? What do you have? You got more than 2.
Yeah, we have almost 3.
Almost 3. Well, you got more than that up here. Well, we thought we'd use this to power our lights. Well, this would only have powered 1/20th of our lights if we hadn't done the daylighting. But 92% of the electric lighting was displaced by daylight. So I only needed this PV to do 8% of the electric lighting. Therefore, a $20,000 system did what $200,000 would have done otherwise. Efficiency makes renewable energy affordable. The more efficient we are, the less of the renewable energy you have to buy in the first place. So you can put these things together with passive solar heating, daylighting, solar water heating, solar electric. You get zero energy houses, zero net energy houses. Even up in the state of Maine. This fellow has his own webpage, which is just solarhouse.com. You can follow him along. He's very proud of his house. On the left-hand side are the solar water heaters, which provide for the radiant heating of the house. Here's the solar electric, and it's got natural lighting, natural ventilation. We know how to make buildings that create as much energy during the year as they use. Now we're getting all sorts of building materials that make it easier, like curtain walls. So we can have buildings, these big glass walls can be solar electric, as you see in this particular building. Putting it all together in a remarkable building, the Durst building in 4 Times Square is 47 stories tall. All the windows can be open, in case you doubted me before. All the offices are daylit. Solar electric spandrel glazing on the upper floor that makes electricity. That glass you're looking at makes electricity. But they also have 2 200,000-watt fuel cells in the building. So when the electricity goes out, it doesn't make a difference. People go around and working in the building. So they have guaranteed reliable electric service. And built for the same cost as conventional construction in the same area. Net additional cost for everything you just saw, zero. Because of the benefits of whole building design. They had sold or rented every square foot of this building before they started building it, because people got the reliability. And not long after the building was up, 9/11 went off happened. And this building is on 45th Street or so. And on some of the TV shots of the World Trade Center coming down, which were long-distance tele shots, this building was pictured. And the electricity went out in lower Manhattan everywhere, except in this building. What a combination. Putting it all together at Sonoma State University, you're in a remarkable building. You're in a remarkable program. And Lucky and others have got plenty of time in your speaker series here to tell you all about this remarkable building that you're in. And what it shows, as Rocky mentioned at the beginning, you can see the way I used to come here. Here's my little electric car. And I'd plug it in right outside there. And I loved it, because then during the daytime, your roof was charging my car so I could go home. And it showed a nice synergy between the two. Beautifully daylit, beautifully naturally cool. Nice. Putting it all together in Cupertino, California, the First Center for Environmental Studies is the building we're working on now. David Deppen, sitting in the back, is the architect of record and responsible largely for virtually everything that you see in this picture. This is an artist rendering. We had a groundbreaking 2 weeks ago. The construction drawings are finished. The building was gone out to bid. The building will be occupied sometime in mid-1985. And so the latest measurements of the building, latest simulation analyses, start with a base building that meets the national code. Our energy code is better than that. The most recent calculations show our building. This is just for electricity use. This shows a 36% reduction in electricity use by the building just from its design. And it turns out the total energy use, the Title 24 comparison, Dave, you saw his email, is also 36%. So we beat the thing we're going into PG&E for, is 36% reduction of energy use in the building over these stringent standards just from design of the building. And then you turn on the PV. And the PV brings it down so it's over 50%, and boy, do we get LEED points for that. So this is a LEED registered building. It's LEED Gold, good and solid. And we still look hungrily at LEED Platinum. We probably won't be able to make it in our budget. But we're right in there. And if I could put more PV, if I can just get more money, so I can do more than just part of the roof, then I could bring this down to here. So the thing is, the point is, if we can make buildings like that in this area, and especially new campus buildings, why would we ever do otherwise? Why would you ever do otherwise in this kind of building, or that kind of building? And to finish this, we've now reached the critical crossing. That's a real crossing. Oh, cold, go back. Cemetery Lane and Power Plant Road is a real crossing in Aspen, Colorado. And what it says is if we continue to have this mentality that to meet growing needs of society, we've got to build more power plants, hang the emissions, don't worry about CO2, hang the cost, hang the lost money, hang the everything. Okay? Both our ecological systems and our economic systems are going to go down cemetery lane. They really are. We have to get away from that power plant mentality. We've got an awful lot of wonderful and interesting political stuff going on right now. And polls consistently show that it doesn't matter what party you're in. You want renewables, you want efficiency, next natural gas, and you don't like the other things. So any candidate, Republican or Democrat or Green, I am a member of the Green Party, by the way, but I'll vote Democrat if Ralph Nader tries to pull another stunt like he did before. Any party, if you support sustainable design in buildings and have an environmentally responsible energy policy based on renewables, you will get extra votes. Okay? But the policy depends on how we will see this relationship between the economy and the integrity of the earth. You can't sell the earth to drive an economy, because after a while you're going to run out of a resource, a pretty darn important resource. And you can't sell the future to drive the economy. But these are both real pictures that I just photographed. Boy. Okay? We're passing the consequences of today's energy policies onto our kids. You can't do that. Whatever impacts we're going to get from our energy use, we need to experience them now. But there's a time delay in the CO2 interaction and the greenhouse gases impact on the earth. So our kids are going to be experiencing all of these economic issues that go with it, and food issues, and war issues. Our kids. And to say nothing of the issues that go on with passing the unsolved problems of nuclear power production, nuclear waste. Okay? So let's define a new patriotism. Reduce international tensions and pollution from energy. Provide jobs, energy resource security, and energy cost stability for our children by using the inexhaustible resources on our own land. And let's make that patriotic. That's a patriotic thing to do. We can wave the flag, that's great. Okay? It's a new kind of patriotism. We're really obligated to start that renewable energy transition now. But it takes leadership. And we have leadership. We don't have enough. We don't have enough. But we occasionally have these jewels of people who really are able to see these visions and who really contribute, whether it's in the university classroom or as policy people. We have enough of them out there to make the difference, but we need more. And I hope I have solicited you to join the ranks. The goal is clear. To live in harmony and sustainability with the earth, you need to realize that we no longer require the earth to nurture us and support us. Who's giving birth to whom in that picture? We have to nurture the earth. We have to renew its capacity to provide for sustainability for future generations. So one really big added ingredient to sustainability is that we have to see restoration in that. We have to restore the impacts of the past as we move on our sustainable path. Treat the earth well. It was not given to you by your parents. It was loaned to you by our children, and boy, we passed a lot of junk onto them already. Let's not do any more.
Out of time, but I want to invite any of you who have questions or comments for Don to come on up to the front of the room, and we can have a small